Hi everyone, my name is Basat, and today I'll be talking about PINT or Probabilistic In-Band Network Telemetry. And this is a joint work with people from Harvard and Queen Mary University of London. And PINT has really been enabled by this trend of programmable networking devices that we have now. And since we have these networking devices, we started writing papers about them, saying, look, now we can do some cool stuff. But actually, this is now becoming a reality. So we see more and more companies that are actually placing these programmable devices in production networks. And one of the killer applications for these switches is telemetry, right? And telemetry is about knowing what's going on in the network. So I want to know everything that's going on with my packets. So for example, I may want to know, is there a congestion or a queue buildup somewhere in the network? I may want to know, do the paths taken by the packets conform with my policy? Like maybe I want them all to go through a firewall, right? And another type of question is, can we increase the rate at which some connection in the network send traffic without creating queue buildup somewhere, right? So to that end and others, the INT protocol was proposed. And INT stands for In-Band Network Telemetry. And the idea of INT is conceptually simple, right? So the designers of INT thought, okay, so we want to collect some information like a switch ID, let's just add it to packets, right? So let me show you what it looks like. So we have this path, and the first hop on the path, it's called the INT source. It adds to the packet something that's called the INT header. And the idea here is that this header would tell the other hops on the path what information we're trying to collect, like maybe the switch ID, right? So it also adds its own switch ID and sends it to the next hop. The next hop reads the INT header, figures, okay, we're collecting, switch IDs. Let me add my own and send it. This way, the packet goes all the way to the last hop, which removes this information from the packet. So this protocol is transparent to the sender and receiver. And now that we have this information, we can figure out, in this example, the path. Right? So let me give you a few use cases for telemetry. The first is congestion control. So just like on the road, if there's too much traffic on a single route, then there's going to be congestion and there's going to be delays. Right? So congestion control is about fine-tuning the sending rate of the different connections in the network, so that's overall, we won't cause congestion at no link in the network, right? And it turns out that a state-of-the-art solution for congestion control, it's called HPCC, and it's running in production in Alibaba, is using INT to collect queuing information from the network, and it uses that to fine-tune the send rate, right? A second use case is path discovery. And it is that there could be many different paths leading to the same destination. And I want to know things like which path did my packets take, or what routing rules do they follow, or more general, do all paths conform with my policy, and things like that. A third use case is for network debugging. Right, so I want to identify switches or links that have high latency. And for example, there can be an imbalance where one path is really loaded while the other one is underutilized, and we want to shift some traffic. And this can also be done using telemetry. Right? So INT is really general, right? Like you can basically collect everything that's available to the switch. You can collect latency information, you can collect queue information. It's already running in production in major companies, but it's also pretty expensive. And the reason is that this information bits that we add on each hop adds up, and it becomes a problem. And if you think of collecting even just like one information type, like the switch ID, if you want to know the path, then every switch would add 4 bytes of information to the packet, and this overhead increases multilinearly in both the number of information types and the length of the path, like the number of hops. So let me tell you why this is an example. So in life before INT, right, if you take the maximal transmission unit, like the largest size a packet is allowed to have, and other than a few bytes that is used for the header that we use for the routing, everything else would be the payload or data of the packet. Now, what happens when you enable INT is that you have to provision enough space on the packet so that the switches can add in their information without exceeding this maximum size. And this means that we have now fewer bits for the payload, for the data. So if I want to send the same amount of information, I will need to send more packets, right? And we did an experiment in which we add this overhead packets, right? So the x-axis here corresponds to adding 1, 2, 3, 4, or 5 information types on standard fat tree topology. And the y-axis is some metric of how well the network is performing. It's called normalized goodwood. And what we saw is that even if you add just like one information type, like the switch ID for path tracing, it already costs quite a bit. And if you want to run HPCC, this congestion control algorithm I talked about, you actually need 3 different types of information to tune the standing rate. And this would cost you even more. And if you want to run HPCC while collecting the path information, it will set you back even further. So it really adds up, right? Second issue with this added information is the switch processing time. And the idea is that the switches have a fixed bit rate in which they can serialize and deserialize information. So if we have now packets that are larger because of the INT information, they would spend more time at the switch. And from our calculation, every information type that you add to the packet would cost you about 1% increase in switch latency. Another problem is the collection cost. And what I mean by that, if you think of a network, we have many switches, we have a lot of packets going through them, they all generate information. And then we need to move this information to a centralized location. It's called the collector. And the problem here is that it really is a lot of information, right? And in practice today, people are running INT only on a part of the data in the network, on a part of the traffic. And this is just because the collection cost is that high. Okay, so to that end, we designed PINT. PINT is probabilistic INT, probabilistic in the network telemetry, and the goal is to minimize the number of bits we add to packets. And our insight in PINT, like the reason why we believe we should do that, is that a lot of the applications that are using telemetry don't actually need all of this information that INT generates. They need some aggregate form of this information. And if we can do this segregation in the network at the switches, we won't need to send all this information to the collector. Right? And our code is open source if it's interesting to anyone. But let me try to first explain why we believe a probabilistic approach is the right way to go. And in very roughly, this probabilistic techniques I'm going to talk about trade the number of bits you add to each packet at the, like they reduce it at the cost of approximation. And you can think of approximation like something in this figure, but there are different types of approximation we use in PINT. One is we do some numerical approximation of like the latency measurements, right? And the idea is that it's often not really important to know what are the exact latency numbers. What is interesting is to know when the latency is too high or when there was significant change in latency, and we can capture that. Another type of approximation is that we may require multiple packets to read the information out of the network. So if you think of discovering the path, then INT would add all the switch IDs on each packet, and now you know the path from a single packet. But if we want to reduce the overhead, we can spread this information across multiple packets, so it would be a while before you know the right path. But it's also fine because usually flows like connections in the network have multiple packets, and even if you assume that they have only a small number of packets, it's already enough to reduce the overhead by quite a bit. What are our techniques here? So we use global hash functions, and we use them everywhere, including the algorithms. So for example, if we run multiple queries concurrently, like maybe congestion control and path discovery, we want the switches to implicitly agree what type of query they should run on the current packet. Right? Another technique is we approximate real valued numbers like latencies to reduce the number of bits we need. And also we use coding to spread information across multiple packets. And all of the use cases I mentioned, they all use some subset of these techniques. So let's go back to the congestion control example. Right, so I told you that HPCC, this algorithm, is using INT, right? And the idea is that it captures several information types from each hop. And then the signal that it uses, so for every hop, it collects 3 different metrics. It combines them somehow using this function f, and it checks what's the maximal value, like which switch is the most congested, right? What we do in PINT is we move the computation of this function f to the switches. Well, we cannot exactly do that because the switches are constrained. We can do some approximation of this function at the switches. And now we can track just the maximal f value along the path, so we don't need to collect all of the queuing information. And this saves a lot of bits, and we can further approximate it to reduce the number of bits and so on. And also in PINT, we do probabilistic rounding so that we would get the right signal in expectation. And now the sender, after receiving a few of these feedbacks, can look at the average and find out just the right sending rate. Okay, let's go to path tracing, right? So INT does that from a single packet. It just carries all the switch IDs. But in PINT, for example, one thing we can do is we can look at the subset of the switches on the path and just put these on the path, right? But actually, we can do even better than that. We can use coding to mix up the subset of switches together on a single packet, and this reduces the number of packets we need to read out the path. And we can even do this with a single bit, which sounds weird, but again, like it's only a matter of how many packets we need before we can read out the path. So we can do this even if we add just one information bit on each packet. And what we saw is that even with a single bit of information, PINT already improves over the state of the art. So let me give you some motivation for why we use coding, right? And this is going to be like a toy example where we only have 2 switches on the path A and B. And if we think of a baseline that just samples one switch ID, right, to reduce the overhead, then it will get some switch ID on the first packet, like maybe A. But now, on average, it would require 2 packets before it can get the other switch ID, which is B in this example, right? So on average, it would require 3 packets to read out this path. Now, think of an alternative algorithm that uses coding, and instead of always sampling one switch ID, with probability 1/2, it's going to sample one switch ID, and with probability 1/2, it's going to write the bitwise XOR of A and B. Now, what happens is that if the first packet carries some identifier like A, right, then the number of packets we need before we can figure out that the second identifier was B reduces significantly. And the reason for that is either we get B and we're done, or, which something that also happens, probability 50%, we would get the bitwise XOR of A and B. And in this case, we're also done because B equals the XOR of A and A XOR B, right? So on average, we would need only 4/3 of additional packets to figure out the second hop, and this reduces the number of packets overall. So PINT solves the overhead issues. We now but by reducing the number of bits we add, we reduce the good to degradation if we want to collect telemetry, and we also reduce the switch processing time. And with that, I will conclude, and I'll be happy to take any questions. Thank you.
Thank you for the great talk, Ran. I actually forgot to introduce Ran before the talk. Ran is actually a assistant professor in the CS department of UCL. He was a postdoc at Harvard before that and received his PhD from Technion. Ran is here to answer our questions. Let us check if there are questions on the Slack channel. While we wait for more questions in the Slack channel, I think I'll go ahead and ask some questions. Ran, great talk. I was curious about your path tracing example that you presented, right? So if I understand it correctly, in PINT, with the path tracing use case, you need to look at multiple packets to say which path the packets actually took. So I was wondering if there is a problem in the flow where the flow is like just short-lived, it just was able to send only a few packets, after which it hit a failure or something like that. Would the original in-band network telemetry will be able to give you the exact information of the path, whereas PINT will not be able to because you don't have enough packets? Is that a problem? Is that a problem in practice?
So you got it right. So in PINT, you cannot, if you use coding, you cannot read anything from a single packet. And then if you have flows that are short-lived, then you need to understand what's the minimal number of packets you are willing to assume that a flow that you care about has before you can read out the path. And this is all about, like, if you assume that a flow has at least 5 packets, we can use that. If you assume it has at least 2 packets, we can use that. If you don't assume anything, we cannot really reduce the overhead at all.
Mm-hmm. So more generally, right? So one of the questions I was wondering is, are there class of applications where probabilistic nature of PINT would not be very helpful, that you need the exact information to be reproduced? Let's say you're doing some forensics or something like that, where you cannot live with probabilistic data. Have you seen some applications? I don't know about those applications.
So I think, like, in some cases, you may want to ensure that all packets conform with some policy, right? Like you don't want a single packet to get to a destination without going through a firewall or something. And in this case, you cannot run PINT, like you shouldn't. But I think for most cases, it's not a requirement that you have to make sure that every packet follows it, and then you can benefit.
Yeah, makes sense. Yeah, and the final question that I had was about the overheads, the compute overheads that the PINT approach has on the switches. Does that prevent any sort of, like, how much is it, and does that prevent like implementing other things on the switch, or does it interfere with the existing functionality in the switch?
So I think all of our algorithms either use none or a very minimal amount of state, like use very little switch memory. What they do use, though, is like they require some operations. This is why we need to run it on a programmable switch. And depending on how good the performance you want the algorithm to make, the more resources they would need, like the more computations per packet they would need. But I think in most cases, they would require at most like 10% of the number of operations per packet it can do.
Yeah, thanks. I think we have one other question from the attendees. I don't know who that is. Can you please unmute and ask?
Yeah, it's me.
Yeah, go ahead.
It's probably me, if there's just one. I have a question. Techniques that use sort of piggybacking on communication to measure things generally suffer from the fact that the amount of information depends on the amount of traffic that happens to be there. This was encountered for rate control by Mellanox in RDMA years ago. And the question is whether your technique aggravates the situation or is kind of orthogonal to that.
So I think, like, in general, there are 2 ways that people are running INT. One is they piggyback the information on packets like what I described here. And the other one is using what's called postcards, where the switches, if they detect that some information is interesting, they would directly send it to the collector without piggybacking it on the packet. And I think like the same algorithms we use in PINT, you can also fit them on the switches for the postcode mode, and then you wouldn't need to piggyback things on the packet itself.
Okay, thank you.
Do we have more questions? Let me quickly check. No, I don't think we have more questions in the Slack channel. Please free to post your questions there, and I think the authors can answer offline. Thank you, Ranbin.